Welcome everybody. So we're starting this mini course, which will be given jointly by Simon Thalabard from University of Nice in France and myself. I'm Alexei Mailybaev. So just organizational part is that it will be every Wednesday and Friday, and it will be always here, almost 2:32 at 15, except with only one exception. Exception is next week. So the one just 17th of January, which is in Auditorium I, same time. So Auditorium I is just the one in front. So remember that there will be also lecture, but it's just different place. So this is the first part. Normally our plan is we have every lecture has two parts with short interval. So interval we take t, right? So interval should be before 4. Yeah, so we still have t. Okay, so essentially what we are going to tell about is the definition and role of hidden symmetries in turbulence. So the structure of the course will be that first two lectures will be given by Simon. So we will switch. So the first lecture will be given by Simon, and the goal of these lectures is essentially give a kind of introduction to the theory of turbulence. So kind of state of art in turbulence. Certainly it's difficult to give it in 2 lectures, and it may seem a bit fuzzy, but there are reasons for that. The reason is that physical side of turbulence in the sense of equations of motion is quite clear. So this is essentially Navier-Stokes equations with some equations so far, but essentially the equations of motion are clear. So what is unclear is not really how to solve, but explain the properties of the solutions. So essentially the open part of turbulence is essentially mathematical. So Simon will introduce the theory of turbulence, which often seems confusing from the first sight, and the reason is that the theory is actually not well developed so far. So many things are heavily underdeveloped, starting from extremely basic things. So just the very existence uniqueness of solutions is one of the millennium problems in mathematics, right? So many things are not clear. At the same time, the equations are posed mathematically in a reasonably clear way. So the questions that we need to solve are easier to formulate. So this will be first lectures, and then we will discuss. So the first, then we will focus on one of the properties of turbulence, which is intermittency, which is in fact one of the most complicated features of the turbulence, and we will we will show how to make connection between intermittency and hidden symmetries in different contexts. So there will be toy models, there will be fluid models, and then we will also discuss more abstract relations which are related to group theory and representations of the groups and so on. So those will be different aspects. And we kind of hope to do this in 8 lectures. So kind of our intention is to make it understandable. So that's why we really ask your contribution of asking questions and stopping whenever you still understand something. So please be free to ask whenever you like. Okay. So then, this week is just introduction to the turbulence, so the kind of state of art in the turbulence, and then and so on. So, oh no, you don't need it. Right? So how we switch it?
Okay.
I think that if you want to ask a question, it helps if you ask it with a microphone, which is kind of not extremely important, but if you ask a question without microphone, it will not be recorded. So that's the difference.
So it's possible as well. Exactly. Well, okay. Thank you, Alexei, for the introduction to the mini course. So indeed, the mini course is called officially hidden symmetries in fluid mechanics. So today and on Friday, we are not going to talk about the hidden part. Hidden is for weeks after. Like this week, we are going to essentially to talk about symmetries, fluid mechanics, and viscosity. And that will be like a very gentle introduction to basically the three components of this talk, and in particular to turbulence. And so to begin, the topic of this first lecture is simply incompressible fluid mechanics. Some basics. And so, as far as we know, the relevant equation in that case are called Navier-Stokes equations. And so, what are the Navier-Stokes equations? Well, essentially, we can write it as the evolution, the PDE, which is the evolution of a velocity field, which we'll call U, under the action of pressure, and some viscous term here, and forcing. And there is 1/4 So here, what are the different terms? So essentially, U, which is a function of space and time. So it's essentially a function that we would like to be from R to R3, or from domain D to R3. So it's a three-dimensional vector field. Okay. The pressure P is a scalar. So it's a field which depends on position and time, which also lives in a given space D, and also takes some values in R. X here, so this is the domain. So X is in D, which is an element of R3. Okay, so we have an ID to discuss three Navier-Stokes exclusively. And there are various parameters which appear here. So ρ0 is the density of the fluid. And as far as we are concerned with it, it's constant. Nu is the viscosity, the kinematic viscosity. And the last bit is this F here, this term, which can be thought of as some type of forcing. It mimics in a very, so it can be gravity, for example. If you think about a real fluid, it can be also the action of boundaries or the spoon on your coffee. So just a force which is given. And as far as we're concerned, we will be so F. We can think of F as a constant force false, or essentially constant. Yeah. Could not be very important. And so this is the first equation. So this equation here basically expresses the conservation of momentum. So we have two guys that we want to solve for, but we have only one equation, so because there is one which is missing. And the one which is missing is known as the continuity equation. It will just be a condition on U, which tells that we are only interested in those velocity fields which are divergence free. And this will be the continuity equation. So those two equations form the Navier-Stokes equation, and as far as we know, they are one of the best model the most minimal model we have to generate turbulence, and they also seem to be relevant to describe real fluids, which is kind of interesting. Just for a moment of history, those equations are quite old, and so on an arrow of time, I think they come. The first trace of it is in 1762, and they were first written by Euler, but in a very simplified situation when U equals 0. Okay. And the introduction of viscosity only happens a couple of years after. It's a story which essentially goes from 1821 to 1855, with first Navier and then Stokes. And essentially, if you read a bit about the history of fluid mechanics, it seems like those two names are the ones which have known the posterity, but the equations have been rediscovered many times in between those two dates by people like Cauchy, Poisson, Saint-Venant. But basically, all this area is about the nu strictly greater than 0. Okay, and so basically that's why we when nu equals 0, we talk about the Euler equation, and when nu is greater strictly than 0, we talk about the Navier-Stokes equation. And for history, I can only recommend a book which is World of Flows by Daigel. For those interested in the history of fluid mechanics, even before Euler, including the story by Bernoulli, it stops with in the 20th century, actually. Okay, so perhaps one can say something about the rationale of those equations. Why are those equations, in a sense, natural? Why do we think they are true? We think they are true because, in fact, they have a very simple interpretation in the Lagrangian frame. So basically, the Navier-Stokes equation are only the Newton's principle expressed in the Lagrangian frame. So basically, what it means is that if we take a fluid particle, as far as this entity can exist, so imagine a point which has a small extension, say dx, dy, and dz. The center of mass here, so that's x, okay? And the center of mass will obey an equation which is dx over dt is u of x to the t and t. We say an initial condition here. Okay. Then basically, this equation tells you how you can relate u along the trajectories to all the surrounding forces. So basically, the Newton principle, it tells you that d over dt of u times essentially rho 0 will be given. So this is an acceleration, okay? And so the change, the variation of this guy will be given by essentially, of course, this term here, f, which is here. So it will be f times rho 0. So I will put it like that. So that's, for now, only there is no field involved. But because there is a field, there are the combined action of the surrounding fluids. So this involves, in particular, action of the pressure field. So, for example, on this side, you have a minus p, which appears at position, if that's position x, at x plus dx over 2. And so if you combine all these effects, this is what will give you this term here with a minus because of this direction here. So we have a minus grad of p. Okay? And so basically, if you stop here, you're at this level. Divided by rho, indeed. Yes. And if you want to include some viscous effects, then you need to basically include another contribution, which essentially will involve also a normal contribution, but also a contribution which allows essentially to shear the fluid. And this object here, they are known as the Stokes stress tensor. And the effect here can be written as essentially this type of term, d of sigma, where if I write, so I rewrite it with sigma is given by the combined effect of the gradient of u of t times u or 0. So if you write it this way, this term here, usually it's simpler to write it with the Einstein notation. And this term here, it will simply be di of sigma aj, di of uj plus dj of ui. And you see that basically what happens is that we take this operation here. This term will cancel by impossibility, so we will only get a term which is the term which contributes here. So basically, the rationale of the Navier-Stokes equation is simply to say, write the fundamental principle of the dynamics by taking into account all the forces you can think about, including the one which are due to this nu being non-zero. So that's why we have faith, in a sense, in them, because they come from very simple physics. So now that we have said that, we have not entirely specified basically the problem here. So we need to say two things. The first thing is that we need to supplement those equations with some type of boundary conditions for the velocity field. And here we will be very, we'll make our life simple. because this course is entitled Symmetries in Fluid Mechanics. So in order to create to deal with equations which are as symmetric as can be, we need to choose a domain which is as symmetric as can be. And so the domain which is as symmetric as can be is precisely D equal R3. So there is a little catch. So sometimes it will be convenient to basically not have R3, but rather to consider U and P as periodic solution on R3. Periodic solutions with so on each direction with periodicity say L on each direction, period L. So that basically U of x plus n L times the vector will be U of x. And so more than often L will be 2 pi, okay? But if we want to recover this setting, we can just take L go to infinity. So that's a periodic trick, which okay, will be useful in particular to handle boundary conditions. Another thing that we need to say is that we have boundary conditions. Then we need to say about what type of solutions we want for those we want to deal with those equations. And for that, we are going to talk about so okay. Yes. Yes, here, yes, yes. So for the velocity, yes. But then the question, for example, if you talk about transport, you always have you may want basically to have R cube. So you may want to unfold the velocity. So it's more convenient in sense to say, okay, we are working on R cube, but U has some periodicity. Then to say that you are working on the torus and that all the trajectories, especially with this Lagrangian interpretation, will be on the torus. That's.
But yes, it doesn't involve pressure.
Yes, yeah, the pressure as well. Sorry, yes, pressure as well. Yeah. And I will make a comment on the pressure after 5 minutes. So yes. So, okay. So we have the boundary conditions. So indeed, so there is especially when D is R cube, there is some type of ambiguity again. So we are going to follow basically the formulation of the global regularity problem in the as you find it in the Clay Prize website. So basically, there is a paper by Pfefferman, which is quite interesting, which introduced the notion of a physically reasonable solution. Okay, so a physically reasonable solution will be a solution which is C infinity. So U and P will be essentially C infinity on R times R cube. So there is a little catch. If indeed D is R cube, we will also ask that essentially the L2 norm is bounded, so the energy is bounded. We required, so essentially U squared on R3 is bounded for all times. And of course, we can ask the same thing for the periodic domain. Well, that's crucial because then we don't have to handle this condition is essentially to handle boundaries. Okay, we will make also this assumption for the integral on L for D. So D equal R cube plus periodicity. One over D is U square or C 4 times. And so basically, no, in the notation it's not good. L cube and X. Yeah, we're good. Okay, so that's just to say that basically, I want to consider those type of solutions, and the problem is, of course, as Alexei said, we don't know if they exist or not, and the attitude toward this situation in this mini course is that let's pretend that they do. As essentially from observational evidence, it seems obvious that they do. And so for those interested, I can only recommend the paper by Pfefferman on the Clay website, and also there is a blog post by Tao. Well, the post is why global regularity is hard. So if you want to know more about these questions, I just go and check that. So that's basically the framework in which we are working it. And then basically there is one last thing that we need to mention about the Navier-Stokes. So we have here always be working with U and P, but in fact P it's almost a fake it's almost a fake field in this story. So basically, so let's erase that. So the pressure field. So pressure field here, it has to be thought of as nothing but a Lagrange multiplier enforcing the incompressibility condition. And the way we can see it is that, so remember the other equation. So let's assume, without loss of generality, that f is divergent free. It doesn't make any difference. So if we take the divergence of this equation, you wind up with an equation for the pressure field, which is a Poisson equation, which is, so in this form, for example, the Laplacian of P is the divergence of this part. For example, you can also write it in a more fancy way with a trace. It's just manipulation. And so that means that formally, P, well, you just need to invert the Laplacian. So we can formally write it as Laplacian minus 1 apply to basically this object. So this operator, this Laplacian minus 1, it's in fact a green function. And so it introduces some non-locality in the business. So for example, if we look at what's happening on R3, just to give an explicit representation, so on R3, then the pressure field is minus 1/4 pi integral for y in R cube of dy of this guy here. So there is a kernel, which is x, so that's p of x, minus y, times this guy here, div of u grad u in y. It's an ugly expression, but okay. I mean, there is the only comment is that there is an integral here, and there is a kernel here, and this comes from this guy here. And so the good news is that basically you have this u grad u which appears here. So in fact, we can totally eliminate the pressure from the game, and we can write the Navier-Stokes equation. So this one, the NS equation, become so dtu plus this term here. So this term here is here and is here. So we may as well call the global operator acting on U an operator. We will give it a name. Is equal to the right hand side, so the diffusive part plus the forcing. And this guy here, we can give it an explicit expression. So PL, say, applied to a field which we call sigma. Okay, is sigma minus. So we need to take a grad here. Grad times minus 1 times div of sigma. Okay. So basically, take the grad of this, take the gradient of this guy, and you wind up with this guy. And this operator here is known as the Leray projector. And one can observe that basically, if you apply the Leray projector on sigma, then you get something which is homogeneous with sigma. So essentially, we have two derivatives here and two minus derivatives here. So in fact, this object here is homogeneous to what's inside, and this will play some role for what comes next. Any question on this setting? So this is basically the setting on which we are going to work. We need to make a comment because we want to. So this is a setting where we have a finite viscosity. So we want to introduce at least at a heuristic level the phenomenon of turbulence. So now is probably a good time to talk about the Reynolds number. So let's write this equation, the Navier-Stokes equation again. So as far as as we are concerned, so this equation from the physics, so this equation has to make some physical sense. And so, especially, we can remark that from a dimensional viewpoint, all the terms here, all the terms have dimension, essentially, u over time. Which is the same as to say that it has dimension u2 over L. When I talk about dimension, it's really physical dimension. So since this is an acceleration, you measure it in meter per second square. That's what I mean by that. And so the only quantity which maybe is more obscure is this kinematic viscosity here. So kinematic viscosity, nu, as a dimension, essentially L divided by T squared. So it's a diffusion coefficient. Nu is a diffusion and depending on the type of fluid that you are interested in, it takes different values. But usually it's very small, at least for the fluid that we are surrounded by. So for example, for nu is 10 to the 6 meter per second square in water. Size in R. And honey is 10 to the 3. And if you consider, for example, asphalt as a liquid, then it's 10 to the power 5. But I mean, you probably know about this. So people have been doing experiments trying to flow asphalt or to make some drop of basically macadam in a lab. It's the longest experiment in physics. It's been 80 or 19 years that it has been running, and they have 8 drops. And this is because of this very high viscosity. But this is wrong, no? Yeah. So okay, so in order to compare those different situations, so a good idea is to try to, instead of running a new experiment for all those new type of nu, depending on the value of f, a classical idea is to try to rescale those equations in order to make some physical parameters appear. And so the way to do it is simply to introduce so non-dimensional form. Non-dimensional form. So introduce L or D typical scale. U typical velocity. And then, okay, let's write x prime is x divided by d. T prime is t divided by, so again, we want to put a t here, and t is nothing but L over u. D over u, sorry. U prime is u over, let's put a 0 here to make it clearer. Okay. In fact, we don't need to rescale the pressure, but because as we have seen, in fact, it's not really. We could work without pressure, but if we keep it, we have to rescale it as well. And so a good way to do it is also to do it in a way that we are going to get rid of this guy. So we are going to rescale it as P over ρ0 u0 square. And f prime will be f divided by L0 over u0 square. D over u0 square. Sorry. And so if you do that, so if you do this change of variable and you plug that in this equation, you get the a-dimensional form of the Navier-Stokes, which simply read dt prime of u prime plus u prime grad prime of u prime plus grad prime of p prime is equal to 1 over a coefficient times the viscous term plus the real scale force, where essentially this number here is called the Reynolds number. So basically, so if you don't trust this calculation, for those who have not done it, just do it. Yes, there's a question? No. Sergey, no. So basically, this prescaling is also basically one of the first evidence as why this equation might be interested in the limit where this guy becomes large. So it was basically observed by the physicist who gave his name to this number, Reynolds. So this experiments which dates back from 1883. Well, basically, it's an experiment that probably you have all heard of. But it consists of flowing a fluid on a canal which has a diameter d. And so what you observe essentially is that when the Reynolds number is very small, so something when the Reynolds number is over 1, and the streamlines of the fluid are straight. When you increase the Reynolds number to go at something which is of order 100, you see some destabilization of the streamlines. And then when you again take some Reynolds number very large, then the streamline seems to break down. And this is actually what we would like to call the turbulent state. As opposition to this laminar one. So that was observed, again, now quite a long time ago. So just to give an idea, so are those extreme conditions or not? So typically, Reynolds about 100 is you trying to put some sugar in the strong coffee of IMPA and trying to just mix the sugar in it. So that's Reynolds 100, possibly. Reynolds 10 to the power 5 and or even Reynolds 10 to the power 6. This range is rather, we say, Nicolas trying to go from Cantagallo to IMPA to Lagoa on his bike. So you're using Ito bike, so it's not super fast, but still you generate a very large number. So it's really easy to create some large numbers of Reynolds, and essentially, well, since it's so easy to create, This is why we are really, from a physical viewpoint, that's why we are interested in trying to describe this state. And the focus of the lecture is essentially, of this mini course, is to describe this state. And in order to do so, well, we resort to several tricks. And the first trick that we'll play at some point, I don't tell you when, is basically to try to understand these turbulent states using some symmetries. So how exactly we are going to use them, I will not tell today, but what are the symmetries, I will tell.
May I ask a question?
Yes.
Previous section. So you mentioned here U0 is a typical velocity.
Yeah.
But is it possible that in different part of the space, somewhere you will have something count, so that velocity is 0, and somewhere it's very large, so then kind of it doesn't become a constant.
Yes.
Random number become kind of local.
Yeah. So in a sense, yes, you're totally right. This is a very loose definition in a sense. So here, for example, what you would choose here in this situation is, for example, you imagine you can control with your apparatus what you put here, and this is what we call U0. And then basically the fluctuation of velocity, which because turbulence is exactly about fluctuation of velocity. Well, okay, this is basically a matter for the turbulence theory. So this number is just a way to tell you, look, if I can put some numbers here, I appear to see some different states. What exactly we'll choose as U0, it will be clear, or maybe, I hope, it will be clearer on Friday.
Is the difference Reynolds number, it just mean that kind of you have a different, scale on which you see the same things?
Yeah. So I'm not sure I understand your question, so I will give you an answer. And no, but so.
Somewhere in a different part of the space you have different Reynolds number, yes. Then just, I would say, you need a different type of microscope to see the same, or it is really different behavior.
No, so this is really different behavior, clearly. The thing that, so the Reynolds number is a good tool, for example, to make plane fly, for example. You want to design a plane which has some certain size, which encounters some velocity. Then you can make an experiment in a wind tunnel by flowing the input velocity at a higher speed at the cost, but with the benefit of having a smaller plane in your wind tunnel. So that's how you can generate the Reynolds number is a way to generate basically the same type of condition in a laboratory than the one you encounter in real life. Of course, okay, modulo the validity of the incompressible equation in that case. About your question, I mean, it will turn out that we will need clearly statistics at some point to describe the distribution of those scales. And so it's not. Yes, there will be a notion of zooming, and depending on how strong you feel the fluctuation. So there will be something along that line will play a role at some point. So I guess if you want to get some tea, we just can make a small break now, and then we'll talk about symmetries. And so symmetries, so it's 50, yeah, so back at 4 or 5? 4? So let's talk about symmetries now. So again, we are going to talk about symmetries of the Navier-Stokes. Let's put the Leray projection. It will be even easier. I formulated with nu, and it will be easier. And then I would just assume that there is no forcing. Not a big hypothesis, but okay, let's assume that this is the case. And again, we take R cube, full space, without any consideration about periodicity here. And so the observation is that NS, the Navier-Stokes equation, is stable or have various symmetry groups. Which leave it invariant. What that means is that basically, so for a symmetry group, let's call it G. So an element of it's basically an ensemble where if I take an element of this ensemble, then if I take U, a physically reasonable solutions to Navier-Stokes, so P, R, and S, then G apply on U is also a physically relevant solution of the Navier-Stokes equation. So let's list the symmetry groups of the equation. So there are some discrete group. So the first one that you obtain is you obtain it by changing t to t, so you don't change it. X to minus x, u to minus u, and you leave u invariant, and that's parity. And you have a lot of, and then you have continuous group. And now you have a lot of them. So the obvious ones are translation. So you have time translation and space translation. So basically, if you, for the time translation, if you change the reference time by an amount tau, and then you leave all the other quantity the same, well, tau is real, then this is not invariant. So space translation is the same, except that you can change the variable of space by x plus an arbitrary shift. So let's put vector here. And all the rest is the same. And here, rho can be in R cube, arbitrary. So time translation and space translation. So what it means, so just to clarify, it means that suppose I have u nu, u of xt it's a physically reasonable Navier-Stokes solution. Then basically this prescribes a group G of U of x prime t prime. And here there is nu involved, so it's u and u nu. That I can write as u prime of nu prime x prime t prime. Okay? With the rule that basically this is t prime. So it means that basically if I define a solution u prime of x prime t prime is u nu of x prime t minus tau. So u nu is a solution. Then this guy is a solution as well. So out of a solution, I create a new solution. And here, basically, I applied this. So this time translation here means this transformation. So I just emphasize that, formally speaking, there is a minus here, and there is a plus here. So those are not the only ones. So we are besides time and space, we have also rotations. Well, this time t is left invariant, but x change to rotate x. You rotate u, and you have new invariant. And here, O is in a special, is a matrix, orthogonal matrix, with determinant 1. So those are the three which are kind of maybe obvious. Another one which is obvious, which comes directly from the physics, is the Galilean invariance. Well, Galilean invariance basically states that since Newton's third law is a statement about the acceleration, or the derivative of the velocity, you can write constant velocity, it will not change the law. So this is formulated in terms of this translation, this transformation. So x gives x plus u0 times t. U gives u plus u0, and u gives u. And so for the Galilean invariance, so that was for time translation. For Galilean invariance, the corresponding transformation here, which will be useful to write, will be the same thing, will be u prime of nu prime x prime t prime is u nu of x prime plus minus u0 t plus u0. So here the minus is very important. And this is basically this minus here will cancel this plus here when you plug it in the Navier-Stokes equation. So exercise. Show that u prime is prime solves the Navier-Stokes equation. If and finally, so we have those 5 equations which come from physics and which in fact don't really care about the fact that we have we were dealing with fields here. And so there is a last one which will be quite important in the future. And the last one is a form of scale invariance. Well, essentially, what you're doing is that you are changing x to lambda x. and u to lambda h u, together with t goes to lambda 1 minus h t, well, essentially lambda is real, positive. It's better, yeah. And h so is real. And if you do that, then you need also to rescale the viscosity. And the good rescaling is that nu goes lambda 1 plus h. Nu. This is symmetry by scale invariant. And again, so if we write this in terms of the new field that we have, so we have that u prime, so u nu gives u prime and u prime of x prime t prime equal. So again, this is x prime. Okay, so if you want to recover x, it's u nu of x prime over lambda t prime over lambda 1 minus h, that you need to multiply by this lambda h. And this is not applied to nu, but to nu prime. And nu prime here, it's lambda 1 plus h nu prime over lambda 1 plus h. Yeah. So basically, the idea is that you again, the same thing is that out of a solution which you know, which provides a certain solution with a viscosity that you know, you can create a new solution at a given nu prime, which is obtained through this transformation. And so those symmetries, okay, we say, okay, that's just at the moment, it's just a statement. And they will play a role in the theory of turbulence that, well, not only the classical theory of turbulence, but also the hidden one. Okay, so that was for the symmetries. And then what I want to tell about is just a comment on energy conservation. Up. So let's put that again. So if you want to, so yeah, this question is a question which conserves momentum, okay, but it's also, in a sense, also conserves energy. And the way you can see it is just by taking the scalar dot product of this guy with this guy. And what you get is an equation which is it's a local energy budget. Local energy budget, which tells you that so u that's u, this becomes u squared over 2, and then you have the dot scalar product of this guy times u dot u plus red p, equal nu u dot u plus fu. So we just need to massage a little bit the terms. So basically, we are going also to need the incompressibility condition. So essentially, this guy, if you write it in a index form, it's ui uj dj ui plus dip. Okay, and we are going to make use of the fact that di ui is 0. So if you make use of this fact, then the ui and the ui they combine to become a square, and then you can put this guy inside. And the same, this guy, ui di of p, because of the incompressibility condition, it enters. So this is nothing but di of sorry, ui u square over 2 plus and that's exactly the divergence of u times u square over 2 plus p. So that's for the first part. And then you have, so this part we'll even touch. This guy we want to massage a little bit. But essentially, u dot expression of u, it's ui e dj of ui, is dj ui dj of ui minus dj of ui dj of ui. So here again, we are going to make, so that's nothing but the Laplacian of u squared over 2 minus the norm of the gradient square. And so if you collect the different terms, what you get is that in the end, you have dt of u squared over 2 plus the divergence of u squared over 2 plus p minus nu times adaptation of u squared over 2 is equal to minus nu grade of u square plus f dot u. And that's a local energy budget. Well, again, all the derivations and so on are allowed because the u's are as smooth as I want them to be. So now, okay, so we have so this is written in conservation form. And in fact, this is also a term which could be entered in the divergence because this guy is the divergence of grad of u2 over 2. So divergence, and then some terms which are not in divergence form. So if we take an integration over the domain, which for that matter here it will be useful to consider a periodic domain, then these terms will vanish. And the only term which will be left are this one, and this one. So integrating over the domain. Over d, we obtain that d over dt of integral over d of u squared over 2 plus 0 is equal to minus nu times u squared over d, okay, plus over d of f of u. It's so this represents, okay, so the variation of energy. This represents the dissipation. And this represents the injection. And a priori, here, for the type of solution that I am considering, this equation is valid for nu which is not equal to 0. It's also valid for nu equal to 0. For smooth solution, or for which the physically reasonable equation makes sense. And here we have a problem. So imagine so usually, so here over D, and so here I will take to be simple. Let me think of D as a torus, basically of size L by L, that I can divide by D, and I can write this budget in a more physicist way. Let's put it this way.
It's volume, right?
Volume, yeah. Here is D volume. Typically L cube. So basically I have this balance, which is, we'll write it this way. Equal minus nu grad u square plus f u. Just where this guy is just can be thought as an average over the domain. So I have done nothing but to rewrite.
One more.
Yes. So this quantity I want to call I for injection, and this quantity I want to call epsilon u. And so the budget becomes a very simple equation, which is essentially d over dt of u square over 2 is equal to minus epsilon u plus I. So here, imagine that I choose a forcing such that with which I can control the rate of energy injection. So with a constant forcing, it's not obvious how you can do it. But if you think basically of forcing with a random term, like Hito term, then this term we can really control. So let us assume that I equal constant for independent of nu. And then you observe that if you take nu equals 0, so for nu equals 0, the budget becomes d over dt of u square 1/2 is equal to I. So for nu equals 0, it tells you that it's impossible to create a stationary state when you inject energy steadily in the system. That seems very reasonable, in fact. If you don't have any term that dissipates, you don't dissipate. But now, when u is not equal to 0, you have the possibility of a steady state. And in particular, a steady state, so here is no steady state. A steady state implies the balance E equal epsilon nu for all nu, even with nu goes to 0. So you may say, well, okay, but it's not written in the stars that you are going to reach a steady state. But the numerical observations of that we do when you put the Navier-Stokes in a computer, or if you want to compute them by hand as well, tells you that basically, if you wait long enough, this type of equality is valid. Is that essentially the conjecture is that there exists a steady state when for any value which is not equal to 0, for which this balance is satisfied. And so here we have a problem, or rather an interesting phenomenon happening. So the existence of a steady state for all values of nu implies essentially that for all nu epsilon nu equal to I. And so, in particular, the limit when nu goes to 0 of epsilon nu equal to I. But when nu goes to 0, formally, so nu goes to 0, formally corresponds to Euler. And for Euler, physically reasonable solutions do not produce steady state. So we have a paradox, or rather basically a phenomenon which is appearing. So this paradox is called in the jargon the dissipation anomaly. Which means, in a sense, that if you want to describe this limit, well, the physically reasonable solutions to Euler are not the good candidates. So physically relevant quote solutions to Euler are not good candidates. And of course, what this dissipation anomaly tells you, okay, so this type of phenomenon tells you two things. In this regime, essentially, so if epsilon nu goes to E when nu goes to 0, then this means that nu gradient of u square norm L2 is constant. Okay, so it means that essentially the gradient of u square is something which behaves as 1 over nu, which goes to infinity. So gradients, basically, if you look at the stationary solutions of Navier-Stokes in the limit of nu goes to 0, gradient explodes, and Euler becomes totally irrelevant. This state is exactly what we want to describe as a turbulent state. So the limit, where you take t goes to infinity, you get the turbulent, to get a stationary state, nu goes to 0 to get rid of the dissipative term, is what we want to interpret as the turbulent state. And this is what hidden symmetry will be about. Yes?
Is it known that steady states for non-zero mu exist?
No, it's an assumption.
Not even the solution exists. It's not even known that the solution exists.
Yeah, so you see,
The steady state, for example, does not depend on time.
yeah, so the way that we are going to,
So it's easier to prove.
yeah, so the way that we are going to construct a steady state, easy way, inspired from a dynamical system, is you take a physically relevant solution and consider a long time limit. And this defines a measure. And then you have a measure on which you can, okay, assuming some ergodic and homology property, but basically this balance will hold. Yeah, but we'll see that, okay, it will match, yes. Yeah.
Well, this is a.
Okay. Sorry. The turbulent measure, if you want. Okay. Yeah, state is really physical jargon, if you want. But yes, we want to describe an object which is probabilistic, and so in fact we want to describe a measure. And this measure is will be provided by some type of long-time asymptotics on any solution that you can build from the Navier-Stokes equation that you may assume as smooth as you want, if you want. Then the limit gives you something non-trivial.
That's essentially mathematical formulation of what means turbulence. Is it solution of Navier-Stokes equation in the limit t goes to infinity?
Yes, if you want. That's yes, exactly, and that's what. So basically, what we want. So here it was. You see this type of problem with Navier-Stokes appears very soon, and we just take energy budget. Poof! You have a paradox, a type of paradox. So the question is, how do you describe this limit when you don't really know too much about the solutions, and when you want to get insights on what's going on? So this is where basically turbulence becomes, as we say, a field at the intersection of physics and math, and at the intersection of observational science, minimal model, and PD. So that's what we are going to do. So the Navier-Stokes is clearly too hard for us. So what we are going to do in the rest is basically we will try to use minimal models, which produce this type of measure of phenomenology, and for the classical theory of turbulence, what we are going to do is that we are going to construct this measure in a very heuristic way. Heuristic description. And this heuristic description is basically the framework of Kolmogorov 41 and Kolmogorov 62 theory. And that's basically the topic of the next course. But I think rather than beginning, I will just do a very short survey of probability, because we will need it for our next course. So the 15 minutes that we are left with, I will do that, unless there are some questions. Okay. So basically, it's clear that to describe this type of measure, we will need a vocabulary which is anchored in the probability theory. And so I just want to make a recap of this type of vocabulary. Yes. Yeah.
Question about not turbulent matter, but about this paradox.
Yeah.
Basically, paradox is that you get in the earlier question solution where gradient of u is infinity. Yes. Which contradicts all the equations. Yes. But then there is, say, notions like Young measures or such type of objects. Yes. That's where exist attempts to define solution of earlier equation, say in a higher class, not in terms of functions, not in terms of distributions, but I don't know, Young measure. Yes. Which, and in that case, it makes it not a paradox. Yes, kind of you dramatically extend the space of earlier equation, but you kill the paradox.
Yeah, I mean that's basically. That's precisely one of the game in modern turbulent research on the mathematical side. Is basically to say we have an equation. What's the space basically? What's the space so that I don't in a sense I free those equations from those paradoxes. And in particular, there have been a lot of work recently that basically focus on trying to construct solutions to the Euler, which essentially have infinite gradients and all types of other properties that we are going to describe. And the bottom line is that it's not enough to allow for solutions to Euler to dissipate to call them physically relevant. So they are physically relevant in the sense that, okay, you are formally able to dissipate without dissipation, but they are not physically relevant in the sense that they select a solution that is really the one that you would like your strong solution to
Weak solution.
in a weak sense. Yeah, of course. Yeah.
Weak.
Yeah. They are wild.
That's the problem.
Yeah. That's those solutions are wild, and so one of the problems is that there are too many of them. So that's so that's one of the.
You lose uniqueness very strongly.
Yes, so then you need to add something extra
Which doesn't work.
Yeah.
No, and it apparently that. Yeah. And apparently it's not the right way.
It's not
Yeah. But I mean, we know there's We don't know what the entropy principle is for the Navier-Stokes. We don't. Yeah, we don't know what is a good selection procedure, and so we don't know what's the space, and we know how we should really constrain the solution to be indeed relevant for this limit mu goes to 0. But it's clear that we feel that the Euler. I mean, we should not discard Euler because Euler are cool, but they are not. We should not. The message is that sure consider Euler, but don't consider strong solutions to Euler, which is, and the rest is modern aspects of research. So yeah, so on a very much at a very basic level, I just want to mention that we will need a short survey in probability theory just to talk about the objects that appear when we try to describe system in that have some randomness in them. And this is basically the topic of probability theory. As a remark, one can mention that the foundations of probability theory are quite related to the modeling of turbulence, because they were, in a sense, laid back in a book by Kolmogorov himself in 1933, which were just less than 8 years before 1941 theory. And so there is a strong connection between this world and data-driven turbulence. And so what I just want to say is that okay, I want to define what I mean by basically probability space. And so yeah, if you want to describe something random, you need a measure with which you're going to average on. And so a probability space, it will be essentially a triplet, which is composed of omega. It's an abstract space of realization. F, it's represent events, and P is the probability. So as you know, there are strong connections between the theory of probability and measure theory. And so in practice, F is a sigma algebra. So basically, it's a collection of parts of omega, which is stable. So basically, stable by unions, countable, intersection, and complementary. It means that if A, B are in F, then A and B are in F, and A1, A in N in F, then the union of A1 in of AA will be in F, and AC will be A in F, and will be also AC in F. And it has, of course, the empty ensemble and the full ensemble are in F. That's basically the definition of a sigma algebra. So this tells you basically what you can measure. And so the probability is just a function that to any element in your algebra will assign a positive number. So that's essentially P of the empty ensemble 0, P of omega is 1, and that if A1, AN are such that AJ is empty, then probability of A1, A2, and is the sum of the probability of AI, essentially. An event which, if P of F equal 1, then F is almost sure. So that's one thing. And so out of this abstract space, essentially, we define random variables. And essentially, a random variable is an application which goes from the realization space to say, here in our case, Rn will be sufficient, and that transports the probability. So that, for example, such that for all intervals or products of intervals in Rn, so say something like A is A1 En, then the reciprocal image of A is in F.
So you can measure in interval.
So you can measure, basically. Exactly. And basically, this product of intervals, they generate all the objects that you can measure in Rn. And so basically, that's a way that basically you transport a measure from a space where you can measure to another space. And so with that, we can define the law of X. So that's a random variable. And the law of X is something that we can write Px of A, where I is a product, say E1, En, product of intervals. And this is nothing but the probability of the ensemble of realization such that X of omega is in I. Okay? And we write it sometimes as P of X in I. This is a conventional notation. And so if you in particular, if you have intervals, you can look at small intervals. So, for example, you may be interested at writing px of x1 plus dx1 times xn plus dxn. Okay, so the probability that you are in small interval of size dx. So this will be written as p of x in dx. Okay, meaning that each of x1, x2, xn are in dx1, dx2, dxn. And so if you want to define, for example, a density, so we may define a density as small p of x1, xn is equal to p of x in dx divided by dx1, dxn in the limit of dx goes to 0, and this is basically a density. So now that we have a law, we can compute averages. Oh, I forgot. And so this law here, this law of x, p of x, sometimes it's called the push forward. So this is also called the push forward of p by x. And that we can something that sometimes is written as p of x is x p. It's a notation which is quite often used. And it only tells you that, okay, you have a probability space, you have an object that transports this probability space, so you can push this probability in your new space, here Rn, here which is Rn, and which is here convenient to define the law. And so averages. So averages for let phi of x be unobservable on x, or a function which takes as an argument a random variable. And so the average of phi well, you can write it in several ways. It can be an average over the original space, which will be phi of x of omega p of d omega. It's an average over the space. Or it's also an average here on Rn of phi of x p of x of dx. And sometimes, so I think the notations may fluctuate between this lecture and the other lectures, and that is sometimes written as, you can write it as online phi, I think, so the average of phi by the push forward of x. And with that, I think I will stop here, and we will be able to describe the next section, at least a Gaussian vision of turbulence.